Hi, everyone. So today I am going to talk about reprogrammable packet processing engine. It ties in with some of the things that Dan touched on. So a tentative agenda is to talk about this particular product that we are working inside Intel called the Glaciers product family. And I'll talk a little bit about parsing of network packets, what it involves, what it entails, and why we need that function to be reprogrammable. I'll talk a little bit about how Intel's reprogrammable parser looks like and the tools flow associated with it. Something that goes hand in hand with the parser is the modifier that actually does the edits on the packet. I'll talk a little bit about that. And then I'll briefly show the SDK and the software stack for this particular product. So today, for the first time, outside of the development community, the PAE and our close customers, we are going to talk about this particular product. That's an FPGA-based SmartNIC. And as you can see, there are two essential features that we have built inside the FPGA. One is a VirtIO hardware interface, and one is a programmable packet processing pipeline. The programmable packet processing pipeline works on some kind of a match action type of abstraction, that is extract X number of bits from offset Y, compare with a value Z, and if the value matches, execute the action foo. If that is something that we were to build in hardware, that's what we have done inside FPGA logic. The blocks of these are connected by a very high-speed internal switch fabric that was also built as part of this project. This is capable of handling millions of flows. It has features such as connection tracking, not just the net filter type connection tracking, but also some custom features like security zones associated with the connections, etc. The beauty of the VirtIO hardware that we have built is that it plugs in seamlessly with existing driver infrastructure. It does not require a driver upgrade. We are able to handle multiple queues per device. And then those of you who are familiar with the idea of live migration of VM from one machine to another machine, there are some additional logic built inside this VirtIO hardware that facilitates this process. So this is that Cascade Glacier card. So going quickly to my topic directly, packet processing parse graph. What exactly is it? So, those of you who have experimented with state machine, you know that it starts from a start state and reaches some kind of what we call the final state or accept state. In case of network packet parsing, usually that start state is Ethernet, and then from Ethernet, by looking at the ether type field, we conclude whether we are going to next transition to an IPv4 state or an IPv6 state. Within these IP states, we then look at the protocol field to figure out whether we are going to go to the UDP or TCP. That's a very simple packet processing pipeline. But then there could be layers of encapsulation, which will give rise to another layer of Ethernet, IP, TCP, etc. So essentially, a parse graph is a path from the start to finish. For instance, in this diagram below, this is a parse graph. This one is an alternate parse graph, and things like that. Packet processing pipeline, similar to CPU pipeline, usually looks very similar, whether it is coming from Intel or coming from some other vendor. It starts with a packet parser, followed by a packet filter, where based on the parse graph that is looked up, certain rules are applied. Then you have packet modifier, where actual edits are made, such as decrementing TTL, updating checksum, replacing the destination IP with some other IP field, etc. And then finally, there is an egress scheduler. That's what typical packet processing parse graph looks like. The question is, why do we feel that this packet processing pipeline needs to be reprogrammable? What's wrong with just a hardened parser that knows that these are the states and then this is the action to be taken? The problem with that, as an example, I wanted to bring your attention what happened with the OpenFlow. OpenFlow, as it moved from OpenFlow version 1.0 to 1.4, from a period starting from December of 2009 to October of 2013, the number of fields, the number of header fields used to classify packets, that grew from 12 to eventually 41. Along with parsing, we also usually do a packet classification, which essentially means that we extract bits and pieces from the different headers to construct a large key. That large key is used to look up the packet in a flow cache or in similar kind of storage. Now, as you see, packet classifier uses values of different header fields for state transition. Some of these are given here as an example. If we had a hardened ASIC implementation of this OpenFlow classifier, it would have gone through anything from a multi-layer change to at least just a metal fix to accommodate these changes in the packet processing behavior, right? And we know how expensive these things are. For instance, just a metal fix at 14 nanometer could cost hundreds of thousands of dollars. There are other complexities. For instance, cloud service providers are known to experiment with pre-RFC protocols. They also, what they do, and we have supported some of these use cases, is they override header fields with custom interpretations of their own. They may take a GRE 1.0 field, and then they change the interpretation of a particular field. So it's neither GRE 1.0 nor GRE 2.0. It is something like a custom implementation. So for that, we have created this logic that we call the reprogrammable parser. And the key thing here is that the parser is built as a generic state machine worker, where what value to extract from which field, what value to look up, what values to compare to transition to the next stage, these things are all flexible. These things are essentially downloaded within the internal memory by a tool, and that way we can move from a very simple packet processing parse graph to a lot more complex packet processing parse graph. Because what will involve is, instead of initiating a change in the RTL logic, it will just involve someone, for instance, the code that you see in the bottom left side, it's written in the P4 language. For those of you who are familiar with P4, it's a domain-specific language. A customer changes this part of the code, and then we have the tool flow, which will create a binary that represents this new packet processing behavior, and then voila, we start processing packets in the same way. Actually, it is not that simple, because we still have to fix the problem of packets continuously coming, but some packets adhere to the old packet processing rules, some packets adhere to the new packet processing rules. So we take care of all of these in software. But this is an example of a reprogrammable parser that does not involve any costly ASIC tape out or even reprogramming of the whole FPGA logic. Since I said that this is an FPGA-based SmartNIC, I think some of you may have already thought that, okay, then programmability is built in. What is new? What is new is we are no longer talking about FPGA recompilation, because as we understood the requirement of our customer, we realized that in some cases there is no time to recompile the FPGA. For instance, some of these changes have to be made before the flows age out. And so hence this approach of having just changing changing a binary blob that the parser block is able to accept and just move on from there. So this is an example tools flow that a customer will change the P4 source, and then we have a P4 to parser binary generator. Please see that I am not referring to it as a P4 compiler, because we have deliberately kept it out of the actually changing the P4 backend, even though there are other teams under me who are writing P4 compiler. For this particular work, what we do is we just pass it through the regular P4 compiler. We get the intermediate representation in JSON format, and then we massage the JSON format to create this binary. Then this binary table is created, and then that is uploaded to the board. We also have a virtual platform that can be used to debug the changes if necessary. Along with the parser, another thing that needs to be reprogrammable is the modifier. This is the entity that actually makes changes to the packet. So the way, it's two very different design philosophy. We design the parser like a generic state machine worker that can take its behavior from tables downloaded in memory. For the modifier, we took the approach of almost CPU type, again, not with the usual complexity of a CPU, but kind of like a programmable CPU that has opcodes representing these actions, such as decrement TTL, encap, decap, calculate checksum, replace IP with some other IP, etc. Here we use a term called template. So a modifier action template is essentially a particular action along with the associated data for that action. So these modifier templates are downloaded to modifier memory by a tool very similar to the parser tool, almost identical tools flow, so I did not add another slide for that. So what do we do for some of these things? I just wanted to give an example. For instance, decap, essentially all that happens is when the stream gets DMA'd out, it is able to take out certain number of bytes from that. So what gets streamed out does not have the decapped header. And for encap, it would be the opposite thing, where along with the incoming stream, some additional bytes of data will be inserted. For modifications, it pulls data from the DDR memory from the actual packet and makes the modification, again, based on the template. And so this is really what happens in the parser and the modifier. So this is how the SDK for this card and the software stack looks like. We have an embedded Linux, and then embedded or enterprise Linux based on either the virtual use case or the bare metal use case. And we have standard VirtIOnet driver. We have management driver. We have flow APIs that connect to Open vSwitch or OpenStack. And these are the components in the left side that connects to these are the components in the left side that make up the SDK, the drivers, the firmware binaries, the API library, and of course these two configurator tool that I just mentioned. So from the morning we talked about how to improve network performances, and for certain businesses and segments, this just improves the way the business is done. But for the cloud service providers, this is business itself. When a cloud service provider buys a multi-core processor from Intel, they want all of these cores to be used for running their customer workloads. That's how they generate revenues. So these things like Open vSwitch and storage and crypto, these things are what they call infrastructure tax, a tax that they're not willing to pay. So the solution that we have effectively, again, Cascade is the first step, and then we will have Cascade offloads Open Virtual Switch, and then we will have other products from this family that will do storage offload and other things. But hopefully, with this family of products, we would be able to get to a point of zero infrastructure tax, so that the cloud service providers are able to fully extract revenue from all of their cores. That is the kind of the vision. That's the wish, and we'll see how we get to that point. I think that's all I had. So it seems like I started a little bit. I finished a little bit early. So questions?
Please come up to one of the mics.
Yeah, this is Shabazz from Stanford. So you talked about the tax thing, but I think this new NIC that you're building is going to cost more than the existing NICs that you have. So you are already paying a tax in some way, either buying a more expensive NIC or adding a new core on your machine. And the second question I have is, it seems like the idea of programmable NICs is already there, like NPUs and stuff, they are already there. So why spend so much effort in building something new if you can do that with the, say, Netronome NICs or something like that? I'm just curious, what's the disadvantage in using NPUs?
So I think your first question was, if someone is buying this card, then that itself involves some kind of a tax. I think that was your first point. So to give you some idea, from a particular core over a period of 1 year, a typical CSP generates about $1,000 of revenue. So if we are able to offload 10 cores, that's $10,000 worth of revenue. And compared to that, the cost of a card like this is just a very, very small fraction. And that's why the CSPs are pretty excited about this particular product. As far as offloading the infrastructure is concerned, I think there will be many different approaches in many different companies about what is the right way to solve this problem. I myself came to Intel from another company where we are doing a complex NPU. So I probably know quite well the difficulties of programming a complex NPU, and so the whole emphasis here was to make this an easily integratable solution. So I think that's where the main value is.
I have a question about the pipeline stage. It looks like, maybe my understanding is wrong, but it looks like there is a stage in the CPU, embedded CPU as well, right? So when you push the parser code to your smart NIC, at least one stage goes through the CPU module, correct?
No, it does not. So Dan showed two different configurations. One configuration is what we call the virtualized environment. In the virtualized environment, the OVS slow path still runs on the host processor, but the OVS fast path has been migrated to OVS fast path, and VirtIO host interface has been migrated to the FPGA.
No,
there is another configuration, which is the bare metal configuration, in which even the OVS slow path moves to the FPGA, and the CPU only gets involved in the OVS slow path handling. We I mean, these CPUs are, fairly small CPUs, and, if it had to play a role in every single packet, we wouldn't have been able to get the throughput. So no, it is not true that every packet has to go to the CPU.
But how is that FPGA doesn't need reprogramming to support new parsing code?
I could not hear the question.
You said that you don't need to reprogram FPGA when you upload the new parser. How's that possible?
So the way it is possible is the parser is not implemented with a hardwired understanding of this is IP, this is TCP, this is IPv6, etc. It's a generic state machine walker. So all you have to do is change its behavior through a table that is inside the parser memory, and that you just change that table and you get a different behavior.
Thank you.
Hi. You said that the virtual machine would use VirtIO.net. What's the backend for that, and how do you ensure you're compatible with whatever version of the VirtIO.net driver that the virtual machine might be using?
So we have a VDPA solution, and we started with a VDPA user, and we have moved to VDPA kernel. Again, this is kind of outside of the scope of my current presentation, but after this presentation, I can talk to you more.
Okay, thank you.
Can you explain a little bit about the usage of DDR4 in NCAP and DCAP?
Use of what for?
What is a DDR4 that you're using for the NCAP and DCAP?
Can you hear the question?
I'm having a hard time understanding too.
You had DDR4 in your diagram. DDR4.
Yeah,
Okay.
yeah.
DRAM memory, yeah.
Yeah. So what was the question with respect to DDR?
What is it used for?
So part of the DDR is used for flow-related storage, etc. Part of the DDR is left for the use of the two ARM cores because it runs Linux and it requires some working memory of its own.
So the other question is, do you implement the OVS data path offload as well?
Do you implement the OVS data path offload as well?
Yeah, this is the fast path. OVS fast path
okay.
is completely offloaded in FPGA. That's what we do.
Okay.
Hey, this is Pradeep. Since this is an FPGA-based SmartNIC, usually customers want to customize the OVS as well as add some of their functionalities on top of it, right? It's a sandbox kind of a thing, and they invent their own actions. Like, once the OVS action is done, apply crypto, compression, or whatever. So how do you envision that from the user's perspective? How do you add those kind of rules into FPGA, and when they want to add this new functionality, is there no open APIs that you provide?
Yes, absolutely. There is an SDK API that directly hooks to the OVS flow, add, delete APIs. In addition, there are some other APIs for configuration, etc. So yeah, so. First of all, we are not tied to a specific OVS implementation. The moment a new OVS implementation comes, we can very quickly adapt to that. The CSPs have, significant inertia towards changing the networking infrastructure. So some of them have, really old VirtIO drivers and other things. Some of them even have customized OVS but are not willing to upstream it. They want to hold on to those changes, but they just want our APIs to somehow connect to their DPIPs and be able to still program it. So we have thought through and implemented all of these combinations. So we are able to support both customers kind of stuck to an older OVS, older driver interface to someone who is willing to take the absolute new. We are able to support the whole gamut.
All right, that's all the time we have for questions for this talk. It seems like it's a talk that a lot of people are interested in, and I hope that Debashis will be available to talk about it later. Let's thank our speaker one more time.